Okay, so number 10 on page 2. It says which choice represents the slope of the secant line. So we talked about tangent line. Tangent line is if the line intersects the curve at exactly 1 point. But I want to kind of highlight something else about that is not only does the graph, when we talk about tangent line, not only does a line skim the surface of the graph at 1 point, it also shares this exact same steepness of that curve at that point. So you can kind of imagine, even at this point here, it's still a rising slope, and that's going to match the slope of this line. So that's something that we're going to be exploring as we get into the next unit. So so tangent line is if the graph crosses or intersects the graph at 1 point. A secant line is if a line intersects the graph at how many points? 2 points. Yeah. So we see that this line intersects the graph at 2 points. It's asking for the slope. So slope is just change in, so rise over run, right? Change in y over change in x. Now, if you look at these order pairs are not quite giving us the exact y values. These are leaving them in terms of function notation. So let's see, what's the order pair then at this point that will match the notation that we see?
2f2.
Yeah, 2 comma f of 2, right? That just represents some y value at this point. We can probably estimate it to be some decimal, but we know f of 2 represents the y value at that point. Okay, what about this point up here, this intersection?
7.
Yeah, so 7 comma f of 7. Right, so if I want to find slope, it's just change in y over change in x. Now, one option that I can do, I can say f of 2 minus f of 7 over 2 minus 7. Okay, if you want to write that down just to show an option here, it may not be the option that matches, but this is acceptable if it were free response, right? Change in y, f of 2 minus f of 7 over 2 minus 7.
Like if you didn't give us the multiple choice options, like those points weren't exact, if you just put like f2 or f7, whatever.
Yep. So this is perfectly acceptable if it were not a multiple choice. But if you see that this doesn't quite match one of the options here, so what's another option that we have available? Yeah, f of 7 minus f of 2 over 7 minus 2, right? That's another option that we have, y2 minus y1 over x2 minus x1. Yep. Another thing that we could do is we could take this and actually convert it to this option, right? If I just multiply both the numerator and denominator by -1, I'm not changing the overall value there. Whatever I do to the top, as long as I do to the bottom, I can still maintain balance. So if I distribute this through with -1, that does and will end up matching part D, answer choice D. Okay, number 11, same concept here. Which choice represents the slope of the secant line shown? Again, we are not provided the y value, so the best we can do is to leave it in function notation. What will represent this first order pair?
X f of x.
Good, x f of x. What about this second order pair?
X.
Good, so x plus 2 is my input. My output is whatever f of x plus 2 gives me back. Okay, same idea, right? There, I can choose this as x1, y1, x2, y2. If I clean up my expression, I can see it's going to match answer choice B. I mean, technically, I could go a little further than what the answer choice B gives me, because the x's do cancel out, but looks like it's just getting it to the point where we can, right before we simplify. Okay, questions? All right, we're gonna do more review. Let's go to the next page.
You said normally they would simplify, right? The x's would cancel themselves out.
Yeah, we could simplify further if it were not multiple choice.
Okay.
Yeah. Mhm. Okay, everybody good? 10 and 11. All right, so good. All right, so next up, being able to look at a rational function. So rational function just means I have x values above and below in my numerator and denominator. So with these rational functions, typically the graphs kind of have this type of a shape where it's not always going to look like this, but we're going to have curves that where there's vertical asymptotes and horizontal asymptotes involved many of the times for the problems that we're going to see, or the graphs that we're going to see. So vertical asymptotes, the way we find vertical asymptotes are places where the graph doesn't exist, where you can kind of draw an imaginary line, a vertical line that the graph will never cross. So the way we find vertical asymptote, we set the denominator equal to 0, and we solve for x. Make sure that whatever denominator factors we find are not going to match with the numerator. Okay, so if there's a matching factor between numerator and denominator, that is called a whole. Okay, so that goes to the next one here. So if we can find numerator and denominator factors that matches and that cancels out, that's the location where the whole exists. Okay. And then horizontal asymptotes is where we compare degrees between numerator and denominator. So let me just go through these notes real quick, and we can look at these examples one by one. So if my numerator and denominator have the same degree, then the horizontal asymptote is simply the ratio of leading coefficient. Okay, let me give you a quick example. If I have y is equal to 3x squared plus 2 over 4x squared plus 5, notice the x squared and x squared are sharing the same degree. If they do, then we simply look at the numbers that's sticking out in front, and that will be the ratio. Y equals 3/4 is your horizontal asymptote. So I have you sitting in that seat number 5 there. Thank you. If my numerator is less than my denominator degree, then there's still a horizontal asymptote, but it's always going to be y equals 0. Okay? And then if my numerator has a higher degree than my denominator, there is no horizontal asymptote. It's possible that there's a slant asymptote, but really in this course, we really don't have to worry too much about exploring slant asymptotes. But so basically, we just say that there is no horizontal asymptote if the numerator has a higher degree than the denominator. Okay, so let's look at number 9 here. F of x equals x plus 2 over 3 minus x. Yeah, there's a couple more things that I want us to find, but we'll start with what we've gone over here. So if I want to find my vertical asymptote, I'm going to set my denominator equal to 0. And while I'm doing that, I might as well just let's just create a graph. And also, I think it's good for us to we're also going to practice identifying or at least creating a rough sketch for different families of functions. I think that's also a good skill. So we know there's vertical asymptote at x equals 3. We see that 3 minus x is not matching with any factors in the numerator. Again, we can't cancel across addition and subtraction, right? If there's going to be a factor that cancels out with 3 minus x, there must be a 3 minus x up in the numerator, or some version of 3 minus x, maybe x minus 3. But it's got to look exactly the same. Okay, so there's no common factor. There's no holes in this graph, okay, because there's no common factors that cancels out. but we know there's a vertical asymptote at 3, so I'm gonna go ahead and now moving on to holes. There are no holes in the graph. There are no common factors. We're going to see some in the next examples here, but not quite yet. Okay, so vertical asymptote, I'm going to say x equals 3 here. Holes, none. Horizontal asymptote. Okay, so now let's look. We're going to compare degrees here. What's the degree of my numerator? Yeah, x to the first power. Okay, what's the degree of my denominator? Also first power. So degree 1 and 1, they're matching. They have the exact same degree. I'm just going to pull the coefficients. So what number's in front of the x? What's in front of this x?
-1.
A -1. So 1 over -1 is -1. So my horizontal asymptote, HA, is y equals -1. So I'm going to go ahead and create that dotted line. So that's a guide as to where that graph. Now, there's something to know about the horizontal asymptote. This asymptote doesn't really prevent a graph from crossing it. It really doesn't do the job of telling us where the graph's going to cross or not. Horizontal asymptote, the whole purpose is to indicate how the graph is going to behave once it exits the graph. Once it exits from view, where's the graph kind of leveling off? So we know that as it exits from view, it's going to eventually kind of hug closer towards these towards this dotted line. Okay. Now, something else that I think also helps is being able to find x and y intercepts. So I'm going to go ahead and add that as well, y-intercept here. Okay, so the way we find x-intercept is we set the numerator equal to 0. Assuming it doesn't cancel out. If the numerator cancels out with the denominator, then that's a candidate for a hole. Okay, but here we see the x plus 2 is completely, doesn't match anything in the numerator, in the denominator, so x plus 2 is kind of alone. So if I set x plus 2 equal to 0, I get x equals -2. So that's my x-intercept. X-intercept is at -2, 0. So it kind of helps, gives us an anchor point to work with. And then what my y-intercept, all I do is I replace all my x's with 0 and see what comes of that. So every x, if I replace with 0, I get 0 plus 2 over 3 minus 0. I get 2 over -3, which is -2/3. I'm sorry, 2 over 3. 2 over 3 is positive 2/3. So I know somewhere along that y-axis there, I'm just going to make it close to my to the origin there. Now, all your graphs, pretty much a lot of the graphs will have this shape, this kind of a arc along the asymptotes. So we know where this graph is going to live, right? Because these points kind of help us anchor it. We know it's going to be above, and the dotted lines kind of help us shape our graph a bit. So we know our graph is going to kind of have it here. And we also know there's something going to be something on this side, right? How do we know whether it's above or below? What an easy way that we can do this is we can kind of just pick a point that we know is to the right here. So if I plug in something like 7, right? 7 plus 2 over 3 minus 7, that's going to be a negative value. And that negative value is going to have me sit over here. Okay. So, and typically they're kind of across from each other like this. And these dotted lines kind of give us a way to shape our graph without having to look at every order pair.
I know how you know, like, it's like, I understand now, like, since you're explaining how, like, it's like below, like, the
Mhm.
horizontal asymptote.
Mhm.
How do you know which direction it's like going to, like?
Well,
like, for the
it's always, yeah, the arrows are always going to go away from the center. So that maybe that kind of helps you a little bit. You know, it's always gonna push away from the center of the graph.
And then how do you know how many, like, different, like, lines are on the graph? Something like this, or,
You mean the asymptotes here? Or what do you mean lines?
like, oh, sorry, like, the different, like, the two different, like, on this one, for example, there's like two different, you know, like.
Right, two different arcs. Yeah,
Arcs, yeah.
typically that's the case. You're gonna just typically have two arcs, especially if there's only one vertical asymptote. But if there's two vertical asymptotes, that's an indication that there could be three branches.
Okay.
Yeah.
This is like interpretation.
Yeah, yeah. Right. So I think the more that we see, the more comfortable we're gonna get. But yeah, typically if there's only one vertical asymptote, we're not gonna see more than two branches. It's gonna be two branches. Okay, but number 10, we're gonna see something that may be a little bit more involved. Okay, so here, y equals 4x minus 4 over x squared minus 9. Let's go ahead and factor as much as we can. We didn't really factor anything for number 9 because it's already in factored form. But here we can do some cleanup, right? So numerator, I can factor out a what? 4. Right? Denominator is the difference of squares. So perfect squares, I can break them into two binomials, right? So x plus 3 and what? X minus 3. Okay. Now, if you look between numerator and denominator, do you see any duplicates between any of the factors? No duplicates, nothing cancels out, there's no hole. Okay. If I don't see any matching pairs between numerator and denominator, we know there's not gonna be any hole. Okay. Yeah.
If there was like a -4 on the bottom.
That's not good enough for it to be a factor. When I talk about factor, it needs to be a matching variable. So it needs to be like x minus 1, or x and x. Exactly the same, yeah. The 4s is just the coefficient. The 4s would cancel out if there's a 4 in the denominator, but that's not going to indicate that there's a hole. The hole is always going to be, it's always going to be involving a variable matching. Okay, so vertical asymptotes. How many do you think we have here? 2. We have 2 factors in the denominator that don't cancel out. So we're going to have 2 vertical asymptotes. If I set both numerator and denominator go to 0, now, going back to my original expression, okay, now whenever you want to find horizontal asymptote, don't look at your factor form. Sometimes factor form may not give you a clear indication as to the comparison between the degrees. Look back at your original expression. So let's compare degrees here. What's the degree of my numerator? 1. Denominator is degree 2. Which one is higher? Denominator. Therefore,
No.
well, hold on. If my numerator is less than my denominator, 0, y equals 0. Okay, so if the numerator has a higher degree, if it was x squared over x, then there will be no horizontal asymptote. But because the denominator has a higher degree, there's still an asymptote, but it's always going to be at 0. So make sure that if you indicate asymptotes, don't just say 3, -3, and 0. Make sure you're naming those lines. X equals 3, x equals -3, y equals 0. These are not single values. These are actual lines, equations of these horizontal and vertical lines. Okay, x-intercept. I can set my numerator equal to 0. If I set my numerator equal to 0, what do I get? X equals 1. Yeah, x equals 1. So x-intercept, the 4 goes away. So 1, 0. Right? That's x-intercept always has a y value of 0. And then y-intercept, replace every x with 0. I can go back to my original expression. Maybe it's a little bit easier. If I take away all the x's, anything connected to the x's, what's my y-intercept? 4 over 9. Yeah, the negatives cancels out. So 4 over 9, that's close to 4/8. That's like a little bit more than a half. Yeah, you could. I like to have everything in factor form just so I can convince myself that there are no holes that cancels out. But yeah, you could definitely leave the numerator alone and you will still get everything the same.
I think if we factor, would that like help us later on when we learn like more factor?
Yeah, I would say always look to factor because it just helps you see things a little more clearly. It simplifies, um, uh, allows the comparison to be a little bit cleaner, I think. Okay, so let's go ahead and draw our asymptotes here. So 3, -3. I have my X and Y intercept. That kind of gives me an idea how my graph is going to look. There's also a horizontal asymptote right at 0. Now, again, the horizontal asymptote is not going to prevent any graph from cutting across. Okay, it's really there to show us how the graph is going to behave as it exits from view, but it's not a line that prevents us from going through. So here, you see these asymptotes here, these asymptotes and these lines kind of indicate that the graph is going to kind of have this these shape here. And I know that there's going to be something on this side as well because the asymptote, I'm expecting 3 branches. I want to kind of know where they go. So if I pick a value, let's say like 6 or 7 somewhere here, I just want to know whether it's positive or negative. If I pick something like 6, I get 24 minus 4 over 36 minus 9. That's a positive value. So positive value is going to have to live in this region. And these asymptotes kind of gives me an idea how my graph can live. That's the only way I can get my graphs to hug the lines. And it's always going to be in that kind of a curved branch. Okay, if I pick a value, let's say to the left of -3, let's say -5, I'll get -20 minus 4, that's negative, and then 25 minus 9, that's positive. So negative over a positive is negative. And if I want something in the negative region, it's got to be over here. So that's enough for me to just do a really rough sketch as to how that branch is going to look. Okay, let's do one more and then we can move on to something else. Okay, number 11. All right, so let's go ahead and factor everything that we can because that allows us to see comparisons a little bit cleaner. What can I do with the numerator? Factor an X, what do I get?
X, that's X.
Okay. Denominator,
X.
good. I can factor an X out. We may have to do a little bit more, but that's a good first step.
You factored 3
Yeah.
and 2.
Yeah, good. So we can do a trinomial factoring, right? 2 numbers that multiplies to be 6, adds it to be -5, -3, and -2. Okay, so here's my complete factored form here. Now, there's something here that we have not seen yet from our examples. What do you notice? We have, yeah, how many holes?
2.
2, yeah, you have X's. There's a hole there. There's also another hole here. Now, when everything cancels out from the numerator, what's left? Good, there's still a 1 here. So I want to make sure that we understand that even if everything goes away in the numerator, it's not a 0, it's still a 1. So our cleaned up expression is 1 over X minus 3, but there is going to be some holes that's going to still be part of our graph, even though it cancels out. So I'm going to set both equal to 0. And I got X equals 0 and X equals 2. So these tell me the X value of my hole. I don't know what the Y values are yet, but I do know what the X values are. So I know there's a hole at 0 and there's a hole at 2. Now here's my reduced expression after my holes cancel out. Okay. So this is what my graph is going to be basically, but with the holes involved. Okay. They're very good so far with the reduced expression and identifying the holes. So now the question is, how do I find the y values of those holes? I'm going to insert my x value into the reduced expression, and whatever y value I get, that is going to be a location where my hole exists. So if I insert 0 and for x, what do I get? -1/3. Okay, so I know I can put a hole at that order pair. Okay. All right, if I plug 2 in, -1. 1 over -1 is -1. So I can highlight those 2 points and make sure I have holes in them. All right, am I going to have a vertical asymptote?
Yes.
Yes. What's my vertical asymptote?
3.
3. Yeah. So basically, whatever denominator factor that does not cancel out, that's a candidate for a vertical asymptote. All right. Am I going to have an x-intercept?
No.
No. There's no variable in the numerator. My graph will never touch the x-axis. If I set 1 equal to 0, that doesn't make any sense. And I'm not going to touch the x and x minus 2. That's already identified as holes. Okay, let's compare degrees for horizontal asymptote. Is there a horizontal asymptote?
0.
Yep, y equals 0. Now, my denominator has a higher degree than my numerator.
So with the exception of like the horizontal asymptote, you used like the factored form, right?
Yes, yeah. So I think factored form is going to be the easiest way for you to see things more clearly, because you're trying to find all those things from this term. It's really hard, right? It's a lot easier to see all the different pieces once it's in factored form. What else? Okay, y-intercept. Y-intercept just means replace every x with 0. Yeah, looks like that is the location of the hole. So this y-intercept is technically undefined because that hole is going to cover up that y-intercept. Okay, so none. Because that hole is not going to be defined, but basically it does tell you where the y-intercept would be if the hole wasn't there. Okay, so let's see if we can do a rough sketch of this graph here. Okay, we know there's vertical asymptote at x equals 3. We know there's a horizontal asymptote at y equals 0. We have 2 holes, 0, -1/3. The nice thing about having these holes there, it also kind of helps you identify how the graph is going to look, right? Because the graph is going to have to kind of, it's going to connect through these holes, right? So having these points here, it kind of helps us identify, okay, I know my graph is going to live in this region. It's going to have to hug along these asymptotes, and it's going to have to kind of go through these holes. All right, I meant for this arrow to head towards the asymptote. It's not going to go away from it. And here, my guess is going to be that my graph is going to be up here. But let's go ahead and just choose a value like 5. I plug in 5 or 6 or 7 into my reduced expression. I get 1 over 7 minus 3. That's 1/4. That's a positive value. So that's enough for me to know how my graph is going to live, or it's going to be. Okay. All right. So I'm going to leave 12 and the rest of page 4 for you guys to try on your own. But let me see if I can get through some. Let's see. Okay, let's do this. Let me do 14 with you, and then we'll use the remaining time in class for you to see if we can finish off pages 3. Okay, and I'll put the answers up so you can see how we do. But let's look at number 4. Let me just let's see if we can look at a graph and identify characteristics from a finished graph. So here, my domain is going to be where my graph exists. But there's only 2 things that's preventing my domain from being all real numbers, right? Where are my 2 restrictions?
The asymptote vertical asymptotes.
Vertical asymptotes, right? So basically it's all real numbers except my vertical asymptotes. But let's just practice writing our domain and range in interval notation. So I'm going to say from -infinity to -1. And then there's a break, right? That break, that asymptote is going to cause me to jump to this second branch. So from -1 to 1, from -1 to 1, and then another break. And then from 1 to infinity. Okay, my range is going to be where my y values exist. In my range, I'm always going to start at the lowest y value and move my way up. So what's my lowest y value? -infinity, but there is a break, right? -infinity to -2. Now here's something is, what do we put after that -2 there? Bracket, because it actually touches that point, right? Actually touches that -2.
Is it -2 or +2?
Oh, sorry, +2, thanks. Yeah, it looks like. Okay, thanks. +2. Okay, so now, and then from the +2, it's going to jump until above the asymptote, right? So it's going to pick up where? 3 with a bracket or parentheses. Bracket. Yeah, sorry, parentheses, right? Because it doesn't touch that point. 3 all the way up to. All right, do we have horizontal asymptotes?
-1 and 1.
That's vertical asymptotes, right?
Oh, sorry.
Okay, so I'll say x equals 1 and x equals -1.
I think it's 3 results.
Yeah, so yeah, y equals 3. Yeah, so make sure you indicate the variable there, since that's part of the naming the equation of that line.
Can you write like as like x equals -1, comma 1? Or
Oh, sorry. X equals -1 and x equals, yeah. So you can say this, or you can say x equals ±1. That's fine as well. Okay. Do you guys want to try? Let's see. Why don't we see if we can try 12 on your own and see how far you can get, and then do your best to sketch the graph as well. And if you're wrong, it's okay. We can kind of just use what we gone through with the examples to help you find all the pieces that you need. Then I didn't have a slot for it, but if you can put y-intercept as well.
so I kind of want the heads up the day 2 part.
Oh, yeah,
Just
sure.
like check this.
Yeah.
But you don't draw a union sign? Or...
Comma or union, either is
Oh,
fine.
okay.
Yeah.
Got 17 wrong.
Sorry.
Yeah. And if you're good with page 3, go ahead and finish off those problems on page 4.
I just forgot to cancel out the 2 terms. That's what I
Got
one of
it.
my problems. Right. Well, thank you so much.
Okay, yeah.
It's pretty easy to just like create our own. Versus-
Yeah. I just had the parent graphs here, so y equals x, y equals x.
Okay, thank you.
Okay, so number 12, notice that I cannot really factor anything in the numerator because that x5 squared plus 2, there's no common factor there. Denominator, I do see 2 vertical asymptotes once I get that x squared minus 4 to factor out to be x plus 2, x minus 2. So I set my denominator equal to 0 to find my vertical asymptotes. If I set the numerator equal to 0, I'm not going to get any real number out of it. So there is no x-intercept. Okay, I'll get imaginary numbers, but in this course, we're dealing with a real number system, so we're not going to deal with imaginary numbers much in this course. Horizontal asymptote. If you look at your original equation here, my denominator and my numerator have the same degree, so I just pull the coefficients in front. So y equals 5/3. Which is a little bit less than 2, that's going to be my horizontal asymptote. Again, we said no x-intercept. There is a y-intercept. If I insert 0 in for x's, I'm going to get 2 over negative 12, which is negative 1/6. Yeah.
Since the numerator is 5, like for the horizontal asymptote, I thought it would mean there's no horizontal.
Oh, yeah. So we don't look at the coefficients first. We look at the degrees. The x squared and x squared, that's indicating that the degrees are the same. So because they're the same, we know that the 5/3 is the coefficient.
So if the degrees are the same, then you do the ratio.
Yeah, do the ratio. If the denominator has a higher degree than the numerator, then it's always 0. And if my numerator degree is higher than my denominator, then there is no horizontal. Okay, so if we just pick points on either side, with these asymptotes, we can I kind of have an idea that this graph is going to be a parabola. That's going to be opening down. And then if I pick values on either side, I'm going to see it's going to be in that positive region. So that kind of gives me, because I have two vertical asymptotes, I know there must be three sections of the graph that's going to show up. And the asymptotes really help to kind of help place our graph a little bit easier. Okay. Let's go ahead and try 15 and 16, and then see if we can also finish off with 17 and 18. So 15, 16, see if we can identify the domain and range. For 16, that hole can make things, I guess, a little trickier, but see if you guys can figure that out. But try 15 first. Okay, so 15, the domain, is all real numbers except for the asymptote. So basically, we have to let the asymptotes kind of help split our regions up into three intervals. Range is all real numbers. That middle branch hits all the y values possible. Horizontal asymptote at x, y equals 0, and then two vertical asymptotes at -1 and 3. Okay, 16. The domain has how many restrictions here? Okay, then we're going to have two. Okay, we have the hole, which means that -3 is not going to exist on my graph. But then there's also an asymptote at -2. So that's another restriction for my domain. So I have two restrictions for my domain. -3, so I need to have a break there, and then a break at -2.
Why would you break at -3 if it's a hole?
Because the graph doesn't exist at -3. Right, the hole means that the graph doesn't exist there.
So then why is it part of the domain?
Well, it's not part of the domain. It says that I can go as close to -3, but I can't reach -3. So that's why I break from -3 and I jump to the other side of -3. The same way, I would approach it the same way as asymptotes, right? I can get close to it, but I can never reach that point. So that's why the parentheses protects that point. Now, what about the range? Is that hole going to impact my range?
Yes.
It looks like it, right?
Oh.
But why does it not?
Oh, because the other one goes to.
Yeah, this one, it's kind of hidden, right? But this continues to rise slowly, but eventually it's going to cover all the y values. And it's going to, so even though it doesn't exist at this y value, this branch will cover for that. Right?
It's
So,
negative positive.
yeah, so it's all real numbers. So the range is not going to have any restrictions. It doesn't stop there, right? It just slowly inches upwards towards infinity. Do we have a horizontal asymptote? No, we only have one vertical asymptote, right? Okay, try 17. Okay, so really the easiest way to see the behaviors of these graphs is factor everything out. Once you factor everything out, you should be able to see clearly the relationships between numerator and denominator. Okay, so which option has a vertical asymptote? F4. Yeah, D. Now B also has an x minus 4, but there's a numerator that cancels out with it. So for part B, 4 is not an asymptote. It's actually a whole. It's got to be a denominator factor that doesn't cancel out. That is where your vertical asymptote is. Okay, we'll do 18 together in class tomorrow, beginning of class. Come up and get your phones, and we'll continue with our notes tomorrow. Thank you. Thanks. It's we're getting ice before.
I do. I don't have borrowed. You can keep that one. I have some at home. No, why did you even need a concept food?